An important term that's very often used in many areas and also very often used in engineering subjects is the term system. Examples of systems are operational amplifier circuits, a radio, a bank account, the human body, or a chemical reactor. Systems are usually very complex, and often they contain many variables and measurements that are not of primary interest. Hence, very often we substitute the system by a model. A model is a simplified version of the system which concentrates on the aspects and properties of the system which are relevant for the application. A system S can have one or multiple input signals denoted x1, x2, and so on. The system can also have one or multiple output signals, which we here will denote as y1, y2, and y3. There exist many different systems and models. The following system classification helps to understand the similarities and differences between them. First, it's important to distinguish between linear and nonlinear systems. In linear systems, the superposition principle holds. It says that if input x1 produces output y1, and if input x2 produces the output y2, then the input alpha x1 plus beta x2 produces the output alpha y1 plus beta y2. Let's assume that the input x1 produces the output y1 and the input x2 produces the output y2. Then combining any scaled versions of x1 and x2 will produce a scaled and combined version of the output. However, for nonlinear systems, the superposition principle does not hold. We also distinguish between time invariant and time variant systems. Let's consider a time invariant system in continuous time. The input signal x of t produces the output signal y of t. Then any delayed input signal, such as x of t minus capital T, produces the same output delayed by the same time constant. This is y of t minus capital T. Let's consider again a simple example where the input signal x of t produces the output signal y of t. Then shifting the input signal by some time constant capital T will produce the same output shifted by the time constant capital T. For time variant systems, this property does not hold. We also distinguish between systems with memory and systems without memory. Systems with memory are also sometimes called dynamic systems. For systems without memory, the output y at a time capital T only depends on the input signal at the very same time capital T. However, the output y of systems with memory or dynamic systems at a time capital T can also depend on the input signal at other times which are not identical to capital T. Another important property of a system is causality. The output of a causal system y at a given time capital T only depends on the input signal at times t less or equal to capital T. In contrast, the output of non-causal systems depends on future values of the input signal x. We write this as y of capital T depends on x of small t for t greater than capital T. Next, let's consider invertible and non-invertible systems. Take, for instance, the invertible system S, which, after receiving the input x, produces the output y. Since it is an invertible system, there also exists a system S inverse, for which using the output y as an input will produce the original input x as an output. For non-invertible system, such a system S inverse, or the invertible system, does not exist. Maybe the most important property of a system is whether it is stable or not stable. Several different notions of stability exist, but for us, the most important one that we're going to use in this course is BIBO stability, where a BIBO stands for bounded input, bounded output. For a BIBO-stable system, it's true that any bounded input signal, x of t, produces a bounded output signal, y of t. In contrast, for a BIBO unstable system, at least one bounded input signal x of small t produces an unbounded output signal y of t.